Okay, so we're going to look today at trigonometric models, and I'm just going to review some of the transformations of functions a little bit. So we're going to start off with an investigation of a trigonometric model like this one. This is the sine function. What will the coefficient A do as a transformation to this function? Vertical stretch or compression? What will cause a vertical compression? Perfect. So if the value is between 0 and 1, often we talk about the absolute values. Between 0 and 1, we'll get a vertical stretch. What if it's negative? Reflection. What will the coefficient D do? Or the number D here at the end?
Will it be a vertical translation in units?
D vertical translation D units. How about B? What will B do? Horizontal compression and stretch. Which one will cause the stretch?
When B is less than 1 or greater than 0.
When B is between 0 and 1, we're going to get a horizontal stretch. So just to show that, we can have a quick look at that down on here. So if I increase the value of A, we will see a stretch like this. If I reduce the value below that, we can get a, what have I got? Move my D, that's one. Okay, we've got a compression. If I make it negative, we're going to get a reflection. So there's the values for A. For D, it'll just move it up and move it down. To help us with D, what we want to sketch is the principal axis. So the principal, what happened there? Okay, so here on the D, we get the principal axis is going to be equal to D. This goes through the center of the graph. And this is how much it's gone up. So we notice it goes up back to this principal axis. And there's the same space between the principal axis and the maximum as between the principal axis and the minimum. You can see the graph moves up and down. B. So if we move it to the right, make the value bigger, what was going to happen? When B is bigger than 1? Horizontal compression. We'd expect it to do this. Like it does. And if we go smaller, we're going to get horizontal stretch. If we go negative, we get a reflection, but it starts to look exactly the same as the original. This graph can get confusing because there's multiple correct answers. For instance, if I put this at -1, if I put this at -1 like that, this graph looks the same as if A was -3. No, just monitor the shape of this graph. I'm going to make this back to 1, and I'm going to make this to -3. That looks the same as the previous one. So many of these graphs can look the same, and there can be multiple correct answers for the graph. The value of C, what would C do?
Horizontal shift or translation.
Horizontal shift or horizontal translation. If C is positive, which way does it move? To the left. So watch this point here. Watch this point here. If I make it positive, it's going to move to the left. This is pi over 2. Notice it's moved pi over 2 to the left. What makes this one tricky? what makes this one tricky? Let me see if I can show this. So, if we notice that the peak of the curve here, the maximum, sorry, what have I got? I've got something messing it up here. To make it nice and simple. Right. We notice that this maximum value here is at pi over 2. If I make d pi over 2, where will that maximum go? This is at pi over 2 here. If I make c pi over 2, where will that move to?
Zero.
C.
Zero.
Zero.
So let's make it pi over 2. Have I got minus?
Yeah, so it's minus.
Sorry, I've got something messed up here.
A is 3.
No, that shouldn't be a problem. All right, it's because I've got x minus c. I've got x minus c. So when I make c pi over 2, it's going to move to this particular point. So if I make it minus pi over 2, it goes to where we're expecting it, because then I've got x plus pi over 2 in there.
So it's supposed to be x. So the general formula has x minus c? Or
Yeah. As it does for all of these type of translations. So if I make it minus pi over 2, it goes to here. Now, if I change the period to 2, if I change the period to 2, let me change the period to a half. Easier to see. If I change the period to a half, the A value doesn't matter, so I'll just make that a little bit bigger. So notice this point here. If I make the c pi minus pi over 2, where will this go to? This point. Where will this point go to?
0. No,
Pi over
2.
So everything moves pi over 2 this way, but if you're trying to work out what the horizontal shift is, it's a little trickier because if you're doing it with this point here, it's easy. But typically, when you're doing your horizontal translations, you're doing it with we're going to be doing it with the maximum point here. So here I've moved it back pi over 4. This one goes back pi over 4, but if we're playing with this one has moved pi over 4, but from where? It's moved pi over 4 back from pi. Because normally it's a pi over 2. You first have to consider the fact that the horizontal stretch has moved this point to pi, and then the horizontal translation has moved it this far back from pi. Can I draw a little off? Let's get into this. We'll move on. Okay. So, how can we see the domain and range from the function in general terms? What's the domain going to be? Not the domain. What's the domain? Yeah. So the domain of this function is fairly easy. The domain is x is a member of the set of real numbers. What's the range going to be? Have a go at writing it down. Write down what the range is going to be.
Of this specific? Or
No, this not specific graph, but this graph here. In general terms.
no C? There's a C number?
No. Yeah, but not for that specific graph that's drawn in general terms. Yeah. Yeah. Less than or equal. Don't focus on the one that's drawn, but you're more general. This would be wrong anyway. In terms of A, B, C, and D. I don't know where you're getting these numbers.
So it's plus whatever is plus and minus.
Okay, let's have a look at our answers. How can we find the range? How can we find the range? I'm gonna take some of this. How can we find the range? Alex.
You take it from A and D.
Okay, how do you take it from A and D?
So you do, it's from D minus A to D plus A.
So we need to find the maximum and minimum. If you can find the maximum, that's the maximum part of the range. Find the minimum, that's the minimum part of the range. Let's look at how to find the maximum and minimum. So firstly, this line here, the principal axis. What is the value of the principal axis? D. So this is the line y equals d. It's the easiest thing to do. When you're sketching it and you have a d value, put your principal axis in first. It's the easiest way to start. When you're drawing reciprocal functions and rational functions, you start by drawing the asymptotes. This gives you a guide. For this function, start by drawing the principal axis. This is d. Now, the original function, the parent function, goes one up, one down from the principal axis. So if the function has been stretched, like this one has been stretched by 3, it goes 3 up and 3 down. What we see, and one of the most important parts about this graph, is this distance here, from the principal axis up to the maximum, is A. It's the vertical stretch. And this is the distance minus A. It's the vertical stretch. So to find the maximum would be A plus D. To find the minimum, it would be D minus A. So the range of the function is going to be from D minus A up to and including D plus A. A has a special name for us. We call it the amplitude. We call it the amplitude of the function. The amplitude is half of the wave height. So this distance here is the wave height. The wave height is equal to 2a. The amplitude is equal to a. D is our principal axis. B. Now B comes from this distance here. So where can I do it? I'm going to do it from here to here. So from any point on the curve to where it repeats the pattern. So between two peaks, between two troughs, between two intercepts with the going up in the same direction on the principal axis, we get the wavelength. This is the wavelength. In math, we call this the period. So this is a periodic function that repeats its pattern of every period. So the period, we've seen this word before when we talk about the period equation solving. The period is when the function starts to repeat itself. We have a special formula for calculating the period, and that is that B is equal to 360 degrees divided by the period. If we're working in radians, it's 2 pi divided by the period. This is the most important formula. Let us find this. Okay. Is there an easy way to calculate the y-intercept of the equation and the principal axis? It's y equals d if you don't have a c. Does it make a difference if A, B, and D are absolute A, absolute B, and absolute D?
What do you mean by absolute? Oh,
So the amplitude is given by A. The amplitude is still absolute A. So the amplitude is the absolute value of A. The wavelength is 2 times the absolute value of A. Sorry, the wave height. The period. Notice how the period, so let's switch this one off. The period is B. If B is positive, we hit, let me do a shorter one. We'll set it to 2. So the period here is from here to here. This is the period. The period here is pi. The period here in this one is pi. That's when it repeats itself. You don't have to use, you can use any point. So we can go from half pi to 3 pi over 2. This is a difference of pi. We can go from here to here. This is a difference of pi. So pick easy points. This point here was easiest. From 0 to pi, that's a period of pi.
wait, so what's the difference between period and wavelength again?
They're the same.
Very much.
If I move this to be minus 2, if I change this to be minus 2, what's the period now?
2. Well, it's
So if I go from here to here, it repeats itself. This is pi. The period is still pi. So B is 360 divided by the period, and this is the absolute value of B. There's no difference between whether it's positive or negative. D. Obviously, D is going to matter because it moves it up or it moves it down. If you take away the minus sign, it's never going to move it down. There's a summary of this information given here. So we see the amplitude, the wave height. A useful formula to add to this is that if we want, often in a question, you're usually given a maximum and a minimum value. If you're trying to model a realistic function, you know what the maximum value is and the minimum. So often we work from the maximum and the minimum, and we say that A is equal to the maximum minus the minimum divided by 2. So it's the difference between the maximum minus the minimum. We would absolute this. We would absolute this because we literally want this length here. We want that length, which is maximum minus minimum absolute. And then we halve it, and it will give us the amplitude. The wave height is maximum minus minimum absolute. So for B, we have the formula here for P in degrees, P being the period. So the formula here is that B is equal to 360 over the period, or 2 pi over the period. And for D, we want the midpoint of these two. We want the midpoint of the y values. The principal axis lies in the middle, so it's the midpoint of the y values. So that's given by the midpoint D is equal to the max plus the min divided by 2. That's the midpoint formula for one coordinate. Value 1 plus value 2 divided by, so it's y1 plus y2 divided by 2. This is a summary of the transformations that we've seen earlier in the course that we seem to understand quite well at the beginning of the lecture. I'd like you to do now is take out your graphing calculator and graph this function. We're going to graph it in degrees and make a little sketch. I'll come around and see how you get on with it. Okay, so if we see on the question here, you see the axes are in degrees. So we're going to be sketching this one in degrees. So we get our graphing calculator, we type it in, it's going to look like this. We need to transfer that onto the paper. So to transfer it onto the paper, start by marking where it crosses the x-axis. Then mark the maximum and minimum. So the maximum is going to be here at 90,2. It's going to be down here at 270. And then we can do with a single curve, show our sketch. So this one continues, so I'll just continue it up like that. There's our sketch. Should look like this. Okay, have a go with this one now and find the values of A, B, and D.
-1.
So first up, let's identify the principal axis. Here we can see that D is equal to -1. We identify the amplitude. We can look at this distance here. So A is equal to 3. And then lastly, we need to find the period. So moving from here up to here, that's 180 degrees. So we get B is equal to 360 divided by 180, which equals 2. So our function is y is equal to 3 sine 2x minus 1. Okay. Have a go at sketching this without using your calculator. Start off by drawing your principal axis. So our principal axis, D is equal to 2. Next, identify your period. Our period is 360 degrees. And we have no phase shift, no C value yet. So it's going to go through this point here, and this point here, and this point here. Next, the amplitude is 4, so we're going to go, the maximum is going to occur here, and the minimum is going to occur here. The maximum is going to be 4 up from that, the minimum is going to be 4 down from that. So we can sketch our curve. We might need to get this one in here. Like that.
How did you know where to plot the x points based on knowing the period is equal to 360? Yeah.
So I know that there's no C value, so the first one is going to be here, and then the last one is going to be here, 360 degrees. We don't have a C value. Horizontal shift. It makes it much harder. Wait till that comes. Horizontal shift. I'm avoiding it at the moment, as you may have noticed. We talked about it at the beginning. Generally, we saw it, but we're not actually doing it until in a minute. So, and then there's one halfway between those, which is this one here. Okay, so find the values of A, B, and D for this graph. Straightforward. So let's have a look. What have we got here? So we can see that from analyzing the graph, I'm looking here first. This goes from here to here. These are the most distinct points. This is at 1. This is at -5. What's the difference between those? That's 6. So A is equal to 3. probably where I'm going to start off. I'm then going to count 3 down from here. 1, 2, 3. And this is my principal axis. So this is the line y is equal to -2. So d is equal to, what I was doing there, I was doing max minus a, which is 1 minus 3 minus 2. I typically take that approach because I don't always know at this point whether there's going to be a C value. And it's much harder. This is the best approach when there is a C value. It's to find the maximum and the minimum, find A. Then find the maximum, take A off of that, you've got D. That's the best all-round approach.
How does that change with the C? Because
You'll see. You'll get that. Next up, especially if the D value is not a whole number. What am I going to do next? I'm going to look for the period. So I can see the period from this point here, repeats to this point here. So our period is 4 pi. So lastly, B is equal to 2 pi divided by 4 pi, which equals a half. This is the function y equals 3 sine a half x minus 1, minus 2, is it? Sorry, minus 2. 3 sine half x minus 2. Okay, this question is a lot harder. I shall give you more time to solve this one. Okay, we're going to do this one now. We'll look at the transformations first. It's a bit easier if we're just looking at the transformations. So first up, we can see that the minimum value here is at something comma minus 1. We can see that the minimum value is minus 1. The maximum value is 3. So what is the value of A? A equals the maximum minus the minimum divided by 2. So A is equal to, this is 3 plus 1 over 2 equals 2. You can see it in the graph graphically. You can see here, this is the value of A. We can see the principal axis quite easily. You can see the principal axis here in the graph. This is the line y equals 1. So we can see that D equals 1. Next, we need to find the period. We're given 2 points I've marked off here. So the period is simply going to be 31 pi over 12 minus negative 5 pi over 12. So that's 36 pi over 12, which is 3 pi. The period is 3 pi. This means B is equal to 2 pi over 3 pi, which is 2 over 3. Our last one is the C value. Now you should be able to get 2 different possibilities or multiple possibilities for C. We can see this point here, and this is the distance C. So in this case, this is a negative value of C, and we're coming back 1, 2, 3, 4, 5, 6. So these grid lines are pi over 6s, and we go 1, 2, 3, 4, 5, 6, 7. So C, we can see is C is equal to minus 7 pi over 6. So we can write this function as y equals 2 sine 2 over 3 bracket x minus minus gives us plus 7 pi over 6. You can also find your C value here. Maybe instead of it being moved back to there, it's been moved forward to this one. So this one we can count off to. We've got pi's over 6, so this is 12, this point here is 12 pi over 6, so we go 1 back from 12 pi over 6, and this gives us y equals 2 sine 2 over 3 x minus 11 pi over 6. What's the difference between those two? What's the difference between these? How far apart are these two numbers? We've got 7 pi over 6.
3 pi.
4
No, it's 3 pi because it has to be the total width.
It's 3 pi. It's 18 pi over 6. So 7 pi over 6 minus negative 11 pi over 6 will be 18 pi over 6, which is 3 pi. The reason that you can have multiple solutions is you're just moving the period across. So if we were to change the period of this from that point by 3 pi, it would come to here.
How do you decide which point you should use to find C?
How do you decide which point you should use to find C? It's an excellent question. This morning I messed it up with the other class, and I'm going to explain why. Because this is one approach to find C using I'm using transformations here. You can see me using the transformations, and it's really easy here. But you don't always get to see where the principal axis is. Maybe you're working off of one coordinate. So if we're working off this one coordinate, we can do this with transformations, working off the coordinate. But we have to be a little bit clever. We have to be a little bit cleverer. The reason being, it's not simple. It's where has this transformed from? It's harder. You have to see where this is transformed from. And because our period is 2 over 3, it makes it a little bit trickier where it's transformed from. So I won't do that approach. You can use the approach using that way. There is another technique which is just very mechanical. And I'm going to do that technique now. But before I do it, I'm going to explain to the people this morning why I went wrong. When it comes, you need to learn both, multiple methods. Learn multiple methods.
I know, but
Here I'm writing the answer. No, either of these two. It depends on how the question is phrased. So sometimes if I say find the smallest positive value of C, such that the function is this, and then the correct answer would be the 11 pi over 6.
We're supposed to put E, right?
Oh, we haven't written the D. I'm sorry. Thanks. Plus 1. Plus 1. So I'm going to find the value using this coordinate here. I'm going to find the value. This is one of the more mechanical approaches. When it comes to using this method, use a maximum or a minimum. Don't use any point, use a maximum or a minimum. This morning, I used any points, and that's what got me into trouble, is I used this point here, I think I used this point here, can't remember. I used one of these points like this, and that ended up with 2 solutions. And the reason I got 2 different solutions is one of the solutions was this curve. In this technique, you can't see the difference between them. It comes from this idea from the unit circle. If I'm solving a trigonometric equation, which this technique requires, if I get one solution here from the sine function, I'm also getting another solution over here. So with the phase shift, you can get 2 solutions, and you don't know which one you need to use in order to get the right shaped curve, because the 2 different solutions will be the difference between the blue and the green curve here. Now, from the unit circle, if I'm solving for this point here, the maximum, or I'm solving for this point here, how many solutions do I get? If I'm solving for the maximum, I only get 1 solution. So both sets, there isn't 2 sets that you have to choose from. If you're solving for the minimum, you only get 1 solution. So if you're using this approach, the algebraic approach, you want to be able to use the maximum or the minimum. Otherwise, you'd have to try both to see which worked and produce the value you wanted. So without further ado, what I'm going to do is I'm going to use the maximum. So let me transfer this information across. I've got a maximum of minus 5 pi over 12, comma 3. So far, I know from my transformations that the function is 2 sine 2 over 3 x minus c plus 1. So from the transformations, you can read off the values of a, b, and d easily. If you can't read off from the transformations the value of c, take a maximum or minimum point. It can be any of them. And then insert it into the equation. If you're on your calculator, end solve. You get your value. If you're not on your calculator, you have to do algebraic. I'm going to do it without the calculator. So I'm putting my values in. Now I get 3 equals 2 sine 2 over 3. My x value is minus 5 pi over 12. Let me just check that was right. Minus 5 pi over 12. Yeah, looks good. Minus c plus 1. So I'm going to subtract 1 from both sides. And then I'm going to divide by 2. Well, let me give it more. I'll subtract 1 from both sides. I get 2 equals 2 sine 2 over 3 minus 5 pi over 12 minus c. Divide through by 2. I get 1 equals sine 2 over 3 minus 5 pi over 12 minus c. And what I was referring to earlier, notice that I'm solving here at this point now. This equation here, I'm solving the unit circle at that point. So when it comes to a solution, I apply the arc sine function to this. I say arc sine of both sides. I'm going to get 2 over 3 bracket minus 5 pi over 12 minus c is equal to pi over 2 plus n2 pi. I don't need the n2 pi's. But now at this point, I only get one solution. So by not using any point on the curve, using either one of the maximums or the minimums, you'll get one solution from your arctan or one set of solutions. And then it becomes easy. So rearranging that, I get minus 5 pi over 12 minus c is equal to 3 pi over 4. And then continuing that on here, I've got minus c is equal to 3 pi over 4 plus 5 pi over 12. Go for a common denominator, multiply the first one top and bottom by 3. I get 9 pi plus 5 pi over 12. So that is 14 pi over 12, which is 7 pi over 6. So c is equal to minus 7 pi over 6. And this is what we got when we did the transformations here, minus 7 pi over 6. If I was to add a 2 pi to this, when I solve it here, taking the arc sine function, so here at this step, if I added an n2 pi, the first 2 pi would be the one solution that would give me this one over here, the 11 pi over 6, and then so on.
Where did you get the pi over 2 in the one where you added pi?
This one,
Yeah. Okay.
I'm taking the arc sine of 1.
Yeah.
So what sine of, so here at this particular point, I am solving sine x equals 1, implies x equals pi over 2 plus n2 pi. Okay, have a go at sketching this function and hence sketch the cosecant function. Why is everybody waiting for me to answer your question? Sketch this function, hence sketch the cosecant function. Okay, so first off, I'm going to figure out what the period is. The period is equal to 2 pi over b, which is to 2 pi over 2, so the period is pi. That means the function is going to go through this point, and this point. Next up, I'm going to add the amplitude is 3, so I'm going to go through there, and I'm going to go through there. The function looks like this, and I need to show that the endpoints here are included endpoints. Your graph should not go beyond those 2 points, so there should be nothing over here in the negative region, because you're given a specific domain in which to do the sketch. Next up, we need to sketch the cosecant. So the cosecant function is cosecant of x is equal to 1 over sine x. What's that going to cause? If the sine function is 0, what will happen to the cosecant function?
Undefined.
Undefined. So how will that appear in a graph?
Like an empty circle.
No.
Isn't the period 2 pi?
I've drawn it very badly. Thank you. You're correct. The period is pi, and I've drawn 2 pi. So you're right. I need it like this, don't I? Thanks.
You asked about undefined look on a graph. Wouldn't that be a straight vertical line up?
Yep, it's going to be vertical asymptotes. So we're going to get vertical asymptotes at these lines here, like this.
But it wouldn't be, but because it's just an empty spot, it's not like a asymptote. It's
That's
a,
an asymptote.
what's it called, where it's just one point or multiple points?
No, point, and it's going to be an asymptote. Because as we approach 0, we approach infinity.
Also, it'll just technically be like this.
Why do you draw the asymptote?
Because we're trying to sketch the cosecant function,
So cosecant is the half
asymptotes.
But wait, if cosecant is the inverse of sine, won't that make it the inverse function? What it is, but
No.
Oh.
No, reciprocal functions are not in the inverse.
But I thought
Only the reciprocal
multiply
function has its inverse as a reciprocal.
But I thought if you multiply something to the, or if you raise it to the negative 1 power, that's.
So what is the value of the cosecant function at the maximum? So the value of the sine function at the maximum is 3. So what will the value of the cosecant function be? 1 over 3. So the cosecant is going to go through 1 over 3 here, 1 over 3 here, minus 1 over 3 here, minus 1 over 3 here. As we approach, as the sine function approaches 0, the cosecant function will approach infinity. So it's going to look like this.
Because look, it's flipping, so you're not just putting at the fine points, the whole graph's gonna change. So,
When you're at your maximum, the sine function, this sine function will have a value of 3. So the cosecant function will have 1 over 3, a third. As the sine function approaches 0, the cosecant function will approach infinity. The bigger the sine value, the smaller the sine value gets, the bigger the cosecant value will get. It will look like this. Okay, last question. I'm gonna do this one for you on the board using a calculator. So take your calculator out in your hand, do an applied problem. Press on, start anew. No. I want a calculator and I want a graph. So we're given this problem that the tide height can be measured in the harbour using the trigonometric function shown here. The first high tide, the following graph shows that the height of the water for 13 hours, starting after midnight. The first high tide occurs at 4:30. The next high tide occurs 12 hours later. Throughout the day, the height of the water has a minimum and a maximum. So let's put this information onto the graph. We can see here that this is at 4 hours 30 minutes, which is 4.5. 4 hours 30 minutes is 4.5 hours, and this must be the height of 6.8. What is the period?
12 hours.
12 hours. So half the period is how many hours?
6.
So this has to occur at 10.5, 6 hours after that one, and the height has to be 2.2. We need to start off by showing that b is pi over 6. So how do we do this? We can do this by b is equal to 2 pi divided by the period, which is 2 pi divided by 12, which is pi over 6. Easy. Find the value of a. So the value of a is going to be max minus min over 2. I'll do that on the calculator. Not there. Not there. Here. The maximum is 6.8 minus 2.2 divided by 2, 2.3. D, find the value of D. This D is equal to the max plus the min over 2. So 6.8 plus 2.2 over 2, 4.5. Find the smallest value of C. So I can use n solve for this one. I can put in the equation. So I've got the y value is 6.8. The a value, I calculate that is 2.3 times the sine of our b value is pi over 6. And then our x value is 4.5 minus c, close brackets carefully, plus d, what was d? 4.5, comma, solve for c. So I put in the maximum point and do a solve for this. I was a little confused for us. So that looks well off. Why do you think that's well off? Sorry? Yeah, but why else is it massively off?
D cannot be a maximum, but like it's on the line of the maximum.
No?
You said that the midline was 4.5. The maximum point can be the midline. It needs to be a read.
I'm not in radians. This seems a lot closer.
How is B, the line of B, the same as the maximum?
Ah, it can't be. You're right. That was what was confusing. Like, why are these both 4.5?
That's why it's so off.
That's why it's so off as well. Where did I calculate 4.5?
It's supposed to be the amplitude.
No, that confused me because I'm like, how can that be the same? But that 4.5 is the x value, not the y value.
Oh,
Yeah, I'm like, I've done something wrong here. I've got 4.5 twice. But by some strange coincidence, this is at y is equal to 4.5. And that x value is also 4.5. And that just threw me for a minute. That's why I paused. So this is our value. This is our answer here.
Minus 167.
What we should do, when you get your C value, you can see how careful you have to be with this type of thing. Check it. So I've got 2.3 times the sine of pi over 6 times bracket. I'm going to put this value in, 10.5. 10.5 minus my C value, which is 1.5, close bracket, plus, sorry, outside of there, I want plus 4.5, my D. So there's my function, and into my function, I'm testing to see if my C value is accurate. I want to see it come out at 2.2. I've just verified that my C value and my function is correct. When I put in the 10.5, I'm getting this Y value here. That's a useful strategy. So we've got C equals 1.5. The last thing to do is to do the modeling question. So we need to type all this information in here. And we have, stop that. We have got, what's our A value? 2.3 times the, sorry, 2.3 times the sine of our B value, pi over 6 times x minus 1.5 plus 4.5. So here is our graph. This should be 13. This should be in radians. Our maximum is up at 10, so I'll put this up to 12. So we see our graph looking something now like what it does in the question. Looks like this. For the first one, what is the height of the water when at 12 o'clock? So we can do this in two ways. I can do it here on this screen. In the variables, I'll pull up the function and I can enter 12 into the function, 2.87. On the graph, I can press menu, add trace graph. I can type 12, press enter twice, and it shows the 2.87 there graphically. Determine the number of hours over the 24-hour period for which the tide will be higher than 5 meters. So this graph is only shown up to 13. So what I need to do is I want to have this one go up to 24. I want to draw another graph. I want to add the line 5 meters. So I need to find how much time during a 24-hour period the curve is above that red line. It occurs twice. I need these time periods, but this period is the same as the second period. So I only really need these two values here. I only need these two values. I can find them by doing a intersection trace. My lower boundary here. So the first one is t equals 1.92. The second one is 7.08. The difference between these two over here will be the same as those two. I can also get that with nsolve. So algebra nsolve, press the variables button, pull up F1. F1 of x is equal to 5 and solve for the variable x. Our first one is 1.92. If I scroll up here and I go in there and say find a value bigger than 1.92 or one bigger than 1.93, we'll get our second value. The advantage of this one is these two numbers written here are three significant figures. These two numbers here appear three significant figures, but I can access them and get them the full decimal expansions. So if I just scroll up here, press enter, and then scroll up to here, press enter. This is how long the period is, so that it's above, and it occurs twice in the 24-hour period. So the answer is 10.8, 10.3. The full decimal expansion of the answer, 10.32. So this is equal to 5.16. All right, we're finished there for today.